The design for the Stonecutter's Bridge was determined by an international design contest that concluded in September of 2000. Located in Hong Kong, the high-level cable-stayed bridge was designed by Dissing and Wentling, with contributions from the Halco Group, Shanghai Construction Engineering Group, and Flint and Neil. At its completion, it was the second longest cable-stayed span bridge in the world. The main span is 1,018 meters by a width of 51 meters. The two pylons are 293 meters high with a 24 by 18 meter foot. Owned by the Hong Kong Department of Highways, the bridge design was wind tunnel tested by FORCE Technology and Rowan Williams Davies and Irwin Incorporated. Structural and civil engineering duties were overseen by Oval Rupp and Partners. The main materials of the bridge are steel and concrete, and the bridge has been open since December of 2009, while it is maintained by Alpen Technic.
So for a model in SAP 2000, I started by drawing the bridge deck at the origin and went back and forth on both sides. So we got a bridge deck, which is I drew in to make things easier. It's just a rectangle, a hollow rectangle. And then I drew our pylon, which is made of two different cross-section properties. You have our 4 piers here, and then there are 28 cables on both sides of this pylon, spaced evenly on both sides, as you can see. And then once I drew this first side and had it all the pylons and piers fixed the way I wanted, I copied and pasted and mirrored it to this side and connected it here in the middle. This is, to make things simpler, I just made everything a 2D, two-dimensional shape here, and then applied our forces and loads on this here. This is the undeformed shape. As you can see, the span here is 1,018 meters scaled down. So I believe this is scaled down from 509 meters, and I think the total height of this pylon is supposed to be 298 meters scaled down, to give size reference there. These cables, they're made of strands of 7mm wire, ranging from 400 cables or wires to 138 wires. So to make things easier, I just took like a middle-sized cable and used it for all of them. So the shapes, when we applied the loads, were not quite accurate, but drawing these 28 cables was pretty tedious. So that's what we did for those. So for our loadings, we did a wind loading. We applied those in the Y plane, which I don't think you can see. Going this way is the X, and then up and down is the Z, so the Y would be going into the screen. I applied that to the bridge deck and both pylons and come up with this deformed shape. For the actual loading, you can see that not much is happening along the bridge deck. I assume if we applied to the cables the wind, it would change that, but a lot is going on here with both pylons. The shear is greater here at the top because more of the wind factors in there. And you can also see that with the moment. A lot of is going on here up at the top and in the middle here with the wind. I think some torsional forces would be coming into play with the wind on the bridge, and that's why you see some red there, a lot of moment going, and on these piers as well. Then I also applied a dead and live load uniformly along just the bridge deck, and that gives us this shape here. It sags a little more than it was supposed to. That's just because of the way, like I said, the cables, they're not all the way they're supposed to. I just drew them all in one size. I didn't range from the 400 to the 123 strands. And the bridge deck is just a hollow rectangle instead of a box girder to save time. So you get a little more sag here than what it's supposed to go, but as you can see, not too much. Have a lot of forces here, a lot of stress here on the pylons, and this is the shear force diagram. A lot of, looks like, got quite a bit of shear stress in the piers here. Not too much in the pylons. I think that's because of the way they're spec'd out, pretty thick. And then the moment diagram doesn't look too bad, actually. Not too much going on. A lot of moments towards the base of the piers. That's to be expected. They're all fixed, so a lot going on. Other than that, pretty good bridge.
Before designing the bridge, we had to make sure we chose the correct scale so that the bridge could fit inside the 3D printer. For our scale, we made it 1 to 2 million, meaning 1 millimeter equals 2 meters. To simplify the printing process, we decided to print components to the bridge instead of one solid object. That way, each component could fit inside the 3D printer. To simplify our project further, we only included 4 piers on each side of the main pylons when designing the bridge. To design the bridge, we used a 3D modeling program called SolidWorks. When modeling the bridge deck, I included tubes and holes that could connect together later to give further support to the bridge. For the cables on our bridge, we used fishing wire to connect the bridge deck to the pylons. To hold the components to the bridge together, we used superglue. Later on, though, we discovered that the superglue wasn't holding the bridge deck, and we used a soldering iron at each of the joints to help solidify the deck. We also used the soldering iron at each of the pylons to give them further support. During the 3D printing process, some of the bridge components did not print correctly, so we had to make a few changes to them. Many of the tubes on the bridge deck pieces did not print correctly, so we got rid of them entirely and just glued the pieces together using superglue.
As with any project at the end of a term, time management was one of the largest conflicts that had to be solved. We used collaborative software, and with clear duties in the week-to-week schedule, we completed the project on time. A second conflict was the quality of the model after the 3D printing. With plastic burrs and some misaligned joinery systems, alternatives had to be found. After some hands-on work, other methods were used to solidify the bridge deck. Some slight shimming was done, and the model was completed. If the modeling process had to be redone, the pylons and piers would be printed again. However, a better bridge deck would be made from a long, rigid material so that it is one continuous piece. This project gave us an insight to the process in which a structure is designed, analyzed, modeled, and constructed. It has deepened our understanding of structures and gave us an experience to carry with us into the professional world.